there comes up a new theory. I'll have to teach that. But right now, this is the newest theory that we have. All right. So, what do you remember? We talked about light yesterday. Remember that? You okay with that? And so what they found out was, so we know light has different wavelengths, and what's the relationship between wavelength and frequency again? You have to know that. What is it?
The longer the wavelength,
the bigger the wavelength, the smaller the frequency, right? Now, what's the relationship between frequency and energy? They're directly proportional, right? High frequency, high energy. So of all of the types of light, this is called the entire electromagnetic spectrum. Is that correct? That's called light. And of all the forms of light, then, which ones would be probably the most dangerous because they would have the most energy per photon? Yes.
Gamma.
Yes. So gamma rays are light, and we remember they have that dual nature of light. It's a particle. No, it's a wave. No, it's a particle. No, it's both. You get it? But the particle is called a what? What do you call the particle of light that carries the energy? A photon. So a photon of gamma ray light, each photon would have much more energy than a photon of visible light or radio wave light like that.
Is that chart show, like, is that the limits on how?
As of right now, I'm not a theoretical physicist. Have we ever made a machine that detects smaller wavelengths than gamma? I just haven't read about it. Have we? Do we know one bigger than radio waves? I just haven't read about it. Right now, I'm going to say this is a limit. I guess I'm not quite up to date on if anybody's gotten something bigger or smaller. That's a good question. That's a good question. If it's something smaller than gamma, I'd like to know, how's it being created or something like that. So, anyway, so we did this, and then we found out if you take a look over here, this is a pretty simple equation. It says that the wavelength, that's called lambda, wavelength times frequency equals the speed of light, which is a constant. So these are inversely proportional, isn't it? So if something had a wavelength that was 10 times greater than another wave, if the wavelength was 10 times greater, the frequency would be 10 times smaller, wouldn't it? And because they're inversely proportional. So I don't think the math is, I'm not going to actually do a math problem. I didn't show this to you yesterday. It's actually a glowing pickle. I didn't really, if you want to look online, you can see how people do this. I can't believe that people do this. They plug in a wire to an outlet. And please don't do this unless your parents said, I want to do that, okay? I can't even imagine they're doing this, but can you imagine plugging in a wire and one of the wires, there's two wires in a wire, right? Two plugs, okay. And so one of them, you hook it onto a pickle, or a fork, and another one a fork, and then you stick the fork. I wouldn't even touch the fork, but I wouldn't touch both forks at the same time, but so you put it in there, and it's like it's glowing. It actually makes the dill pickle glow. And if you look online, you'll see people doing this. I've actually never done that. I've watched it on YouTube and that kind of stuff there, but this one has to do with this guy named, in America we call him Max Planck. What would you call him in Germany? Max Planck, right? So if you hear somebody say Planck, that's because they want to be a little more technical. But if I say Planck, is that okay with you? Max Planck. Anyway, so he's, imagine studying an object like a piece of metal, and you heat it, and it gets hot, and it gets hotter, and it gets hotter, and it starts glowing. What's that fancy word that means you're going to glow because you're hot? Very good. Incandescence. So he's going to let this metal get hotter and hotter and hotter, and he's going to measure the amount of energy that's coming off of it. Well, before Max Planck, everybody thought this. All right, you heat it, a little more energy, a little more, a little more, a little more, just like a graph line, just like that. That's what's going to happen. And it didn't. And that surprised everybody. They said, what do you mean? Wouldn't you just get a little more energy, a little more as you got hotter and hotter, and it didn't. And so he and Einstein together, you put them together, they said, light's funny. And the electrons are doing what? I erased this from yesterday. And here's what he found out, especially Einstein. Here's the nucleus. Here's an electron. Again, they're not really going in a circle, okay? And he said that if you give this atom a little more energy, won't the electron just jump a little bit higher and then a little bit higher? And if I had a graph, wouldn't the electron energy just keep going up like this? And that's what they thought. And they found out it didn't, especially Einstein's photoelectric effect, okay? If you give me a certain frequency of light and shine on that metal, no electrons jump off the surface, none. Make it brighter, sorry, no. And only until you got to a certain frequency, a certain kind of light, then electrons would jump off. And if you made it brighter, more would jump off. As a matter of fact, any wavelength higher than that threshold would make them jump off. And you said, what the heck does that mean? Yes?
In the reading, it said that this worked on metals. Does this work on non-metals as well?
You know what? I've never read somebody who did a study with nonmetals. Now, metals have a tendency to have loosely held electrons. That's why they make them good conductors of electricity. So maybe they started with metals because they knew that you'd be more likely to lose electrons.
Okay.
That's a great question. If you want to find it, I've never seen anybody do a study on nonmetals.
Yeah.
All right, so anyway, here's what happens. You would expect the electron to jump a little bit higher level, a little bit higher, have a little more energy, just like a graph. You see that? But it didn't. It says here, if you want to get me to jump, you better give me this much energy or I'm not going. If you can't give me that much energy, I'm not jumping up. And so they said that energy is quantized. So it said, you can do, it's like this, nothing, 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 jump, nothing, 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 jump. And they said to themselves that you can't just absorb energy a little bit, a little bit, a little bit, a little bit. You can get this much, or maybe the next jump is even bigger. And now you need that quantum. I need that much a quantum of energy. Here's a certain quantum, here's another quantum. And so they said it was quantized. And so if you want to go up the row here, you got to go up in steps. And if you don't give me a full quantity, full quantum of energy, I'm not going up that step. I'm not going halfway up the step. You get it? And I guess that's what made everything change. That made everything. That's why they call it the quantum mechanics model, because you have to absorb or release energy in full packets of energy, and they call that a quantum. Are you okay with that? All right. Let's go to the next one. This one, and I'm not going to get into all these equations and things. We don't have time. I just don't have time. Here's what they summarized. Energy is quantized, and it can occur only in discrete units called quanta. That's the plural of quantum, like that. Quantum's one, quanta is plural. Electromagnetic radiation, which was previously thought to exhibit only wave-like properties, seems to show certain characteristics of a particulate matter as well. The photo of this phenomenon is sometimes referred to the dual nature of light. And then they had this other guy, his name is de Broglie. So here's another guy. We had Planck, Einstein, and de Broglie, okay? De Broglie, he's a great mathematician, and I can't understand his stuff. I've seen it. It's so mathematical. I can't even understand it, some of it. But he says, you know what? My mathematics will show that everything has a particle nature and everything has a wave nature. Everything. Now, what's interesting is if the particle's small, if it's small, then the wave nature seems to predominate, and we don't see the particle nature very much. But what if it's something like a baseball? What if it's as big as a baseball? Then it still has a wave nature, but the wavelength's so tiny we can never notice the wave nature of it. We only notice the particle nature of it. See that? So if I get into the little world and I want to look at things like electrons or something, they're going to probably be more of a characteristic of a wave than they are of a particle. And anyway, that guy's name was de Broglie. And again, I'm going kind of fast through here, but I want to get to the main things here. All right, here's the good part. I like this part. I saw this actually being done when I did this. First of all, have you ever done something like this where you shine a light through a prism and see a rainbow? Okay, so you can have a prism, and what happens is the light bends or refracts. Okay, now when it refracts, when it bends, it just so happens that some wavelengths bend more than others. Does anybody know of Roy G. Biv? Which one will kind of pass through the prism and not bend hardly at all, and which one bends a lot? Anybody know which one? Which one is it? Right? Okay, so red doesn't bend very much, and then violet bends a lot, doesn't it? And so when you pass white light, they call it white light through here, then it'll bend, and if it separates, then it's called diffraction, okay? It diffracts into different colors. So reflect, like a mirror. Refract, it bends, the light bends. Diffract means it bends to the point where it separates into colors. Okay, those are your three words there. Okay, so what does that mean? Now, I'm going to set this up for you, and I should have it by tomorrow, I think. What if we took some material like hydrogen, and we had a gas in here, and we exposed it to an electric current? What do you think would happen to hydrogen if I put electricity through it? You say, well, I don't know. This says that it might do nothing. If I only give it X amount of energy, it might do nothing. If I give it more energy, it might be able to make a quantum jump, right? The electrons might jump. And so what they did is, I actually saw this, it was on a show. You know what a rheostat is? It's a dimmer switch. You know what a dimmer switch is? Any of your houses have dimmer switches, you know, you make them? Okay, that's a rheostat in electrical terms. So hook this up to a rheostat. I'm going to give you a little bit of energy. And I let the light, and nothing. And then all of a sudden it goes boing, and I see one color. I see one of these little bars of color right here. One bar. I get a little more energy. Boom, boom, boom. 3 bars. 5 bars. And so what's happening is, why don't I get a continuous spectrum? Why don't I get all of the wavelengths? What's the theory there? Yes?
The hydrogen in the light only lets certain colors go through
Why?
because it's molecular.
Okay. So let's say this is the electron where it normally is, okay? And I give it some energy, and I'm ignoring that. I'm ignoring that much energy. But I get to that one amount of energy, which is exactly a quantum, and then the electron goes to here, but then also it absorbs energy and goes to here. But what happens when it jumps back down? If I absorb energy to jump to a higher level, what happens when I jump back down?
Energy is released.
And if that energy is released in a color that I can see, that's what those things are. One of those beams of light, get it? Now, why would you get more than one color?
There's different layers.
All right, now watch this now. Ready? Okay. Now, when it jumps back down, where can it jump back to? It could jump back to here, couldn't it? Where else could it jump?
Back down.
And then where? Ooh. Now, let me ask you this. Which one would be more likely to be a red light, and which one would be violet? Is it this? Here's a 1, and here is a 2, and here's a 3. Let's do all of them. Let's do green. Red, green, violet. Which one of these, when it jumps back down, would tend to be giving off red light? Ooh, you think you know? All right, Calvin.
1,
Is what?
red,
How'd you know that?
because it's the least amount of energy.
Yes, that's great. So only a small amount of energy was released. So So that would tend to be red light. All right, what about this one versus that one? Go ahead, Calvin.
What, say again, sorry?
That's a 2, that's a 2, and that's a 3.
2 would be the green, 3 would be the
Right,
red.
and then the most amount of energy released, the highest energy would be what? The smallest wavelength, wouldn't it? And that would be violet. So this would be more likely to be violet light, green light, and red light. Now, the story goes beyond this because we didn't know, they did not know what these colors meant for a long time. And they started doing some mathematics and stuff like that, and they started comparing the energies. And they eventually came up with these words that you may or may not remember from 10th grade. Do you remember principal energy levels? Do you remember the word energy levels?
Yes.
Okay, if not, I'm going to do it again. You had your hand up and I didn't call on you, sorry.
Oh, I was wondering, so does hydrogen give off the most colors of light since it has the most principal energy levels that it can go up? Or
Okay,
does-
what I have back there on the back wall, everybody see the back wall? If you were to go back there, I think there's about 10 or 12 elements listed on that back wall poster, okay? If you have a chance to look at that, you'll see that if you gave all those elements the same energy, they would give off different bright line spectrum. This is called a emission spectrum or bright line spectrum. And it's like a fingerprint. That's what I think is neat. Because if you give me this color, this color, this color, this color, you must be hydrogen. You give me this, 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 you're sodium. We have street lights out there, and if I went out to some of your neighborhoods, some of your neighborhoods are street lights. Anybody have street lights that look kind of dingy, not very bright? Okay, some people pass laws, like in California, they only allow those kind, and those are called sodium vapor lights. Now, if I took a, it's called a diffraction grating, okay? Rainbow glasses, okay. If I took some rainbow glasses there and I looked at it, I would see the same colors as I saw for sodium back there on that poster. If I were to go in the gym, that's pretty bright lights up there, isn't it? I don't know if you knew that, but that's mercury vapor. Those are called mercury vapor. There's mercury, vaporized mercury in there, and when they excite the mercury, it gives off a huge amount of light, like really bright, isn't it? But if I looked at it with diffraction grating, you would see the bright lines of mercury. So you can actually identify some elements by looking at their spectrum, their emission spectrum. Yes?
Does the bright lines kind of spectrum tend to get have like shorter and shorter wavelength colors as you go?
No, it has a variety. And so I'll tell you what it means, though. You may get less lines here than you might with another element because, and I'm going to get into this real quickly. All of this took time, but they eventually said, you know what? I think the electrons must exist in what they call energy levels. And the energy level number 1 is closest to the nucleus. And we call that the lowest energy level. Okay. And then we saw there was another energy level and another energy level and another energy level. So let's see if you remember this from 10th grade. As of right now, how many energy levels do we think there are that electrons can exist in? And again, closest, that's the lowest energy level, further away, further away. So how many do you think? I'll give you a clue, it's up here. It's all in that periodic table. How many energy levels? Yes? No? It's right there. It's on that periodic table. Yes? Yes. Ready? 1, level 2, electrons in level 3, 4, 5, 6, 7. As of right now, if they start discovering past 118, I'll have to see what's going on. But right now, we think there are 7 principal energy levels. And why are there only 2 elements here? Because they're the only elements that put all their electrons in the first energy level. I put my first 2 electrons in the first energy level, but I'm the first element to put a single electron in the second energy level. Is this coming back at all? And so if I have at least one electron in the second energy level, you put me in period number 2. These are called periods, by the way. Isn't that right? There are 7 periods of the periodic table because they represent you have at least one electron in that energy level. Get that? What do you call these things? What were they called? Groups or families, right? Groups or families, same thing. All right, so here's where it gets kind of good. This is where I was trying to show you here, and Calvin, you did a great job. What it says here is if you make these jumps, remember when you absorb energy, you won't give off light. It's when you come back down to what they call the ground state. Ground state is what you normally at, right? Is that correct? All right. How do I know that hamburgers have electrons in them? I made some hamburgers last night. How do I know that hamburgers have electrons in them? No, because they're always in their ground state. Okay, just see. Okay. So the ground state simply means that the electrons are where you would find them most of the time. That means they're not excited. They're not excited. So remember, when they absorb energy, they do not give off light. It's when they go back to their ground state or they go back to the next level down that they give off energy. And you asked a great question. Some of the bigger elements, they can jump from level 7 down to 6, can't they? Or how about 7 down to 5? And it gets more complicated because guess what? In level 1, there's only one way to exist in level 1. And we're going to call that in a minute. It's called 1 sublevel. It's called an S sublevel. But guess what? In the second energy level, there's 2 ways to exist. S and P. And I'll show you the pictures in a minute. In the third energy level, you can exist in an S orbital or a P orbital or a D. And if you get in the 4th or higher, it's S, P, D, and F. Now, I will tell you that I found this article. So when you go to college and somebody says SPDF, you say, don't you know what that means? Most people have no idea. So I want to show this to you real quickly. This is the origin of the SPDF orbital labels. And if you want to, we'll take a real quick look, maybe about a minute. Come on. And if you read, I underlined some of the things here, and said down here, the discovery, 1885, blah, 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 4 principal spectral lines of hydrogen. He called these a series of blah, blah, blah. Where am I at? Here it is. Okay, nomenclature, naming. He named the principal orbitals, they're called S, were called sharp. That's because when they said here, when they looked at it, it was sharper. I originally was told that S meant it was like a sphere, and that reminded me that S orbitals look like a sphere, but it actually doesn't stand for sphere. It stands for sharp. And then D is diffuse, and F is fundamental. And what am I leaving out? P? All right, where are you, P? Uh-oh. Am I missing that somewhere? Yeah. Anybody see it? Okay, I don't see it.
Principal, sharp, and diffuse series.
Oh, principal. I didn't underline principal. Sorry. Okay. Okay, there we go. So just in case you want to know where the letters came from, somebody who was looking at spectral lines, sharp, diffuse, fundamental. Okay. So here we go. Let's get into what we're at here. And this is some math. Let's skip that. Let's skip that. Yeah, let's skip that. Yeah, skip that. Yeah, skip that. Okay, let's get to the good stuff. All right, here we go. Now, so why were we getting so many colors? If you look back there, there's some of those elements that you're going to see like 20 bars of color. And they didn't know for a long, long time what that meant. So let me show you what this means here. Which one? Okay. Wow, I actually gave you one that had writing on it. I didn't mean to do that. Okay, let's do it this way. Okay. See if you can you find this one right here? It's way, way back there. All right, what we're going to do is we're going to talk about electron configuration, all right? And I'm going to try to show you some pictures. I should have seen them. Oh, there's one. There's some. There they are. All right, so here we go. In level 1, principal energy level 1. Level 1, and that's called the lowest energy level, the one that's closest to the nucleus. So we have level 1, and then we have these called levels, and then we have sub-levels, and then we have orbitals. Okay, so let's start with that. All right, the energy level number 1 is the closest to the nucleus. It is the smallest volume, and it actually can only contain a maximum of 2 electrons. So it can only contain 2 electrons max. Okay, so where are these electrons located? And they have these things called quantum numbers, okay? The first quantum number is easy. What energy level are you in? What energy level are you in? Okay, that's the first quantum number. Well, the first electron is going to go in a sublevel called S. Now, it just so happens that if you're an S sublevel, there's only one way to be in that, and that's an s orbital. Now, that sounds weird, and wait till I get to P, and it'll make more sense. So if you, level 1 only has an s sublevel, and how many ways can you exist in an s sublevel? 1. You only have one s orbital. Okay, so let me show you what that means. Here's a diagram of electrons, and as you go up, they have a higher energy to them, okay? This right here, 1s, means you're in the first energy level, you're in an s orbital. Now, it just so happens that an s sublevel there's only one way to exist in the s sublevel, and that's to be an s orbital, and there's only one kind. Okay, now, so what's going to happen is, if you're hydrogen, you're going to be there, and I'm going to put an up arrow, and I'll talk about the quantum numbers in a minute. Okay, stay with me a little bit. I don't want to get boring. Somebody figured out that you can put 2 electrons in an orbital. But if you have something that has a charge, electrons have a charge, right? Do you know that anything that has a charge that moves will create a magnetic field? Did you know if I let electricity run through a wire and put a compass next to it, it'll deflect the compass? Because around that wire is a magnetic field created. So anything that has a charge that moves, it'll create a magnetic field. Well, somebody much smarter than me figured out you can put 2 electrons in the same orbital if one is spinning clockwise and one is spinning counterclockwise. Now that's hard for me to draw. So what most chemistry books, they'll put an up arrow and say you're spinning one way. And you put a down arrow, you're spinning the other way. You got that? Okay, so let's try it again. If you're hydrogen, you only have 1 electron. Where are you? What's the address of that 1 electron? It's in the first energy level, and it's in an s orbital, isn't it? And it's spinning, I hereby declare clockwise. Okay, I got you. Now what if you're helium? You have 2 electrons. Where are you going to put them? I know what I'm putting the first one. I'm putting the first one the same place hydrogen did. What are you going to do with the second one? Can I put another one in there? Yeah, if what? If you spin in the opposite direction. So what we say is hydrogen's electron configuration is 1s1. Now that means in the first energy level, in the s orbital, you have 1 electron. Okay, what is the electron configuration And you know, configuration is a fancy word for what? Did you know my room has a configuration of tables? Is my configuration of tables the same as the other room? It just means arrangement, doesn't it? What's electron configuration? Arrangement. How did you arrange your electrons? All right, ready? Hydrogen, 1s1. Helium, what do you think? In the first energy level, in the s orbital, how many? You can put 2. All right. Now, you know what? I can't put any more in the first energy level, and that's why how many elements are in period number 1? See that? 1s1, 1s2, and you're out of room. You're out of room in the first energy level. You can't put any more electrons in there. And that's why there's only 2 electrons. Matter of fact, if I had to make a periodic table, I could see, I've even seen something like this. I could even see putting helium over here. See that? I could see it. But you know why they want to put with these? Because these are all called noble gases, because their electrons are in a configuration that's so stable, they don't want to react. But I can see putting this guy over here, because 1s1, 1s2, but they also want to put them over here because I don't like to react, I'm either. And that's when they want to put them with the noble gases. So I could see a periodic table that puts helium here and also here. That wouldn't bother me if I saw that. Okay, let's go to the next one. What if you're lithium? What are you going to do with 3 electrons? I'll bet you know what I'm going to do with the first 2, don't you? What am I going to do with the first 2? If I'm lithium, what am I going to do with the first 2 electrons? 1s2. Right? Isn't that right? But now, you got another one. Yeah, you're right. I'm the first element that needs a second energy level. Where do we find it? I am the first element in the second period. See? I'm going to read the periodic table. I'm going to read it. Okay, so what's my configuration? 1s2. Say it. You can do it. Second energy level. Hey, guess what? In the second energy level, where do electrons go first? They go into what kind of orbital? An S. Oh, that's interesting. Level 1 had an S. Level 2 has an S. You think level 3 has an S?
Yep.
It does. You think level 4 has an S?
Yep.
5?
Yep.
6?
Yep.
7?
Yep.
Well, now you got it. They all have S's, don't they? Now, there we go. Add them up. 2 plus 1, 3 electrons. Is that you, lithium? Yeah, I have 3 electrons. All right, next one. What's beryllium going to be?
1s2, 2s2.
All right, 1s2, 2s2. That's 4. I got this. I got this. See that? All right, you with me? I know you're tired. Okay. All right, now things get interesting. I didn't do this, but the second energy level is further away. It's got more space, doesn't it? It's got space for a s orbital, but it also has space for this sublevel called the d. And I'll show you some shapes here, okay? It's a coincidence that s orbitals are kind of spherical. Remember, we just found out it meant sharp, but it's also spherical, so I remember that. So 1s would look like this, 2s would look like this, 3s would look like that. Get that? That's what this picture's showing here. What does a p orbital look like? Ooh, you're weird. You're weird. You look like a little dumbbell or something like that. And that's what they are. So anyway, how many ways can you make a p orbital? That's what's weird. And you can have it oriented this way, or this way. So let's try this again. Look at my picture. First of all, in the first level, you only have S. I don't have to worry about P in the first level, do I? But in the second level, and third, and fourth, and fifth, and sixth, and seventh, we got to worry about P, don't we? Anybody have to go to the bathroom? Just kidding. All right, so now, in the second energy level, you have to go into 2s and another one in 2s, don't you? But then what? What takes a little more energy is the 2p, doesn't it? That's why it's a little bit higher up. Get it? So let's try it. If beryllium is this guy, who's the next guy? Who's the next element? Boron. How many electrons? 5. Where are you going to put them? First energy level, s orbital, I'll put 2. What are you going to do with the next 3? Second energy level, s orbital, I'll put 2. Now you got one more. Where are you going to put it? How about that? What are you going to call it? Are you still in the second energy level? Then you better say 2. Are you in an s orbital? No. What are you in? P? Oh, okay. How many are you going to put in there? 1. See? Is this coming back a little bit? If I can get you to read the periodic table, you don't have to memorize all this stuff. All right? I'll show you how to read it. We've got to hurry. Okay, what's the next element? What it? All right, what do you got? 1s2, 2s2, keep going, 2p2. Now, sorry this happened, but there was, I gotta remember, make sure it's the right name. His name was Hund, H-U-N-D. He's much smarter than me. That's why he's in the chemistry books, I'm not. Somehow, he figured out, you want to put it here, don't you? You want to do that? And I don't know how he figured this out, but he figured out that if you put one here, it's not as stable. See, electrons, atoms want to be stable. They want the electrons to be as stable as they can. And he said, you can put another one in the 2p, but don't put it in the same orbital. And so what's going to happen is, this is actually more stable than pairing them up here. Now, that's a good question, why? So we still say 2p2, but in your head, you say to yourself, one of them's here, one of them's here. Let's do the next one. What's the next element? Help me out. Let's see how fast we can get. 1s2, 2s2, 2p3. Where's it going to be? Ah, see that? Okay. Next element. Ooh, it's going to get interesting now. What's the next one? Okay, ready? 1s2, 2s2, 2p what? 4. Where's it going? Okay, see that? When we talk about organic chemistry, we talked about the this having four valence electrons. Remember these? But these were already paired up. You'd think that they couldn't make bonds with them because they're already paired up. But they made I went too far. Wait, no. Did I do it too far? Oh, I'm talking about carbon. I went too far. Sorry. When I had carbon, I had 2 here and 2 here, didn't I? Anyway, what happened is they would make a hybrid sp, an sp orbital, kind of halfway between, right? And they had 4 equal sp hybrid orbitals. Okay, let's move on. Anyway, so here's that one. What's the next guy? What is it? Fluorine. All right, tell me what that is. 1s2, 2s2, 2p5. Okay. And the next guy, oh, it could be special. This could be special. What is it? Is it neon?
Yeah.
Oh, what is it?
2s2, 2s2, 2p6.
Oh, that's something special. Look what I've done here. Look what I've done. I have actually, the second energy level is completely full. And for an atom, that's stability. And what does it mean on the periodic table? I know where to find these guys. If you have 2 in the S and 6 in the P, I know where to find you. You're going to be right here. Everybody who's a noble gas has 2 in the S and 6 in the P. What's the only noble gas that doesn't have what they call S2P6 configuration? What's the only one that doesn't have 8 in its outermost energy level? Somebody said it. Not hydrogen. Helium. And you know what? I only had 2 electrons. So this is the first noble gas, stable. This is the second noble gas. Get it? You get it? Now, that's all you can do in the second level. You can't put anything else in the second level. So in level 2, you can have S and what? And how many different ways can you have a p orbital? 3. Watch this now. Watch. Every orbital can hold 2 electrons. Ready? How many orbitals do you see? How many orbitals? 4. What's 4 times 2? All right. What's the most number of electrons you can put in the second energy level? 8. 1, 2, 3, 4, 5, 6, 7, 8. That's why there are 8 elements in the second period. How many electrons you can put in the first energy level?
2.
That's why there's only 2 elements in the first period. You get that? Ah, so who's the first one to need a third energy level? And where is it located? Where is sodium located?
Next period.
Now, we're going to do a little, you want to do a little shortcut? You guys like shortcuts?
Yes.
It's called the noble gas configuration, all right? I know you have 11 electrons, but you know what? I know what you did the first 10. Yes, I do. You put your first 10 in a very stable arrangement, just like neon, didn't you? So you know what that means in brackets? Your first 10 electrons are just like neons. Okay. Do you have any more? Oh, yeah. I have one more, don't I? What is that at?
3s.
3s1. Ooh, where am I located on the periodic table? Oh, wait a minute, wait. 1s1, 2s1, 3s1. Say it. 4s1. Oh. Don't count you. You should be over here. 1s2. What's this one? 2s2, 3s2, 4s2, 5s2, 6s2, 7s2. What do you call this here? The S block. If you're an element there, your last electrons are in the S orbitals. And how many can the S orbitals hold? And how many columns did I just show you? 2. Look over here. How many are in this block here? All right, ready? P orbitals. How many P orbitals are there at any level except for first? Each orbital can hold 2. 3 times 2 is what?
6.
And how many elements are here? Oh. Look, P1, P2, P3, P4, P5. Oh. We're going to read the periodic table. You get it? And if you can do that, you don't have to play a lot of these games that some teachers have you play these games and how you memorize these things. Okay. Wow, are you done?
Yeah, I just finished.
Oh, really? Okay. I'll take it. Thanks. Wow. Okay, how about, let me think about this. Okay, ready? Watch. 1, 2, 3, 4, 5. Who's this? Who's that? Argon. Noble gas, right? 2 in the S, 6 in the P. Yes? And then something weird happens. Something weird happens after 3P. That's weird. And you know what? Because I happen to know that level 3 has an S orbital and it has 3 P orbitals, but how many D orbitals does it have? I'll give you a clue. Odd numbers. There's only one kind of S. There's 3 kinds of P's. How many? 5 D orbitals, right? And so let me ask you a question before you leave. I know that some of you are really tired. Last question. The third energy level can hold way more. Why did you stop? Why doesn't the periodic table keep going? You should keep going. You got the D orbitals. But where do I know? Where did electron number 19 go? You should have gone in the, not 3S, not 3P. You should have gone on 3D. And so think about it. Where did it go? What? Where did it go? Say it. 4S1. What? You didn't fill in the 3D yet. Well, guess what this chart says? It's easier to go into where? 4S, and then I'll go into 3D. Now, how are you supposed to memorize that? Look at the periodic table. Ready? S, P, what comes after that? 4S. And then you get to a special block. Whoa. Oh, what's that? How many elements are in each one of those? 10? 2 times 5? 10. Okay, see you. You did a great job. Thank you very much.
Thank you.